Well, good afternoon. Thank you all for coming out today. Again, my name is Isabel Hong. I'm my advisor, Dr. Lisa Ely. And my talk is titled Sedentological and Stratigraphic Evidence for Paleo-Tsunami Events at Quirico, Chile. Funding for this research was provided by a National Science Foundation grant, and I also received a scholarship by geoengineers, so thank you. I want to start off this presentation by talking about why study earthquakes and tsunamis in Chile. So Chile is located along an active subduction zone. The Nazca Plate here, roughly outlined, is subducting underneath the South American plate at a rate of about 7 centimeters per year. These red dots indicate locations and years of earthquakes that have occurred throughout Chile based on both modern instrumentation and historical records. In contrast to that, here we have in this second figure, the yellow dots indicate locations where people have actually gone and looked for geologic evidence of past earthquakes and tsunamis. And the blue dots here indicate locations where right after the 2010 tsunami, investigators went to look at the superficial effects of the 2010 tsunami. So these locations were not studied for past events. You can see that in relation to the sites that have actually been studied. They pale in comparison to the amount of seismic activity that has occurred. So there's really a lack of information as to how Chile has been affected in the past, geologically speaking. So here I'm focusing in on the south central region. Here's Santiago, and Quirico, my field area, is highlighted in green. We can also see here that Quirico is in this region of earthquake rupture overlap between the 2010 earthquake and the 1960 earthquake. Here off to the right we have a figure. Here we have latitude off of the y-axis, time in years on the x-axis. We have past earthquakes that have occurred throughout this region. The solid lines indicate instrumentally recorded earthquakes. The dashed are estimated rupture lengths based on historical records. So they're a little bit more fuzzy than those solid lines that we have. So you can see that Quirico has been affected by a lot of seismic activity in the past. And more specifically and uniquely, it has been affected more recently by the 2010 and 1960 earthquake, one that ruptured up to the north, one to the south. So it'll be really interesting to look at the geologic record at Quirico for evidence of earthquakes and tsunamis to see how Quirico has been affected in the past, if it, for example, only preserves events to the north, the south, both, and if so, how? Which leads to my hypothesis, that due to the geographic location of Quirico as the site of rupture overlap, there will be evidence of tsunamis resulting from subduction zone earthquakes to both the north and the south. To test this hypothesis, I have outlined 3 objectives. The first, to locate and describe tsunami deposits. The second, collect samples for radiocarbon dating so I can better constrain the timing of deposition for these tsunami events. And the last, conduct grain size and thin section analysis to quantitatively and qualitatively describe the various units at Quirico. To take a quick step back, talking about the bigger picture, why are we even interested in this type of research? Well, we want to better understand tsunami hazards. So if we look at Quirico, understand what types of tsunamis affect Quirico and how these tsunamis behave, we can perhaps avoid situations such as this here. This picture was taken right after the 2010 tsunami in Chile. The ship has left the harbor, the tsunami brought it inland. And so we want to be able to better mitigate these types of hazards. So to start off, first thing that we did here was we looked at satellite imagery. So this is just from Google Earth, looking for evidence of the geomorphology here. So here we have Quirico, which is a small fishing village, and the modern-day Quirico River is outlined in blue, and we wanted to look for that ideal sweet spot, ideally, where we think tsunami deposits would be best preserved at Quirico if there are tsunami deposits. And we eventually settled on, it's difficult to see here, but this is an abandoned meander of the Quirico River. And we outlined here 2 transects, a transect A, essentially a seaward to landward transect, so that if there was a tsunami deposit, we wanted to see if the tsunami deposits eventually thinned landward. If so, how did it behave? And an intersecting transect, transect B, that looked at how widespread these tsunami deposits would be. We also installed a tide gauge here outlined in this star. to calculate and measure the local mean sea level at Quirico. So to establish the criteria for whether or not we were seeing tsunami deposits, we settled on 3 very basic criteria. The first, that there had to be an erosive basal contact overlaid by sand. The second, that the sand unit had to be widespread and tabular, so it had to follow the topography. The last, that the sand units eventually did thin landward until it pinched out completely upstream. This is a picture that Dr. Ely took right after the 2010 tsunami. This is a block that was dug from the earth and then moved up to the surface to take a better picture. And you can see, just based on the 2010 tsunami, that you can see that rough, erosive basal contact overlaid by this massive layer of sand. So we wanted to look for something like this in the stratigraphy. So to do this again, following those 2 transects, we dug pits and we cored and noted the stratigraphy. We also took samples for radiocarbon dating, grain size analysis, and also lithological analysis of the sand. So we wanted to make thin sections of the sediments and to look at them. So again, just to remind you guys, 3 basic criteria we had: erosive basal contact overlaid by sand, the sand unit had to be widespread and tabular, and lastly, that eventually it thinned out landward until it pinched out upstream. So here we have this beautiful erosive basal layer overlaid by sand here at Quirico. And in total, we found 5 really good sand layers that match these criteria. So sand 1, 2, 3, 4, 5. Additionally, we found a sand layer 6. We're calling that our basal sand layer because it's so massive and thick we couldn't even dig down to the bottom of it and find a different unit. So for now, we have 5 very ideal candidate sands and a basal sand 6. So do these sands actually follow across the topography and the landscape? In fact, they do. So we have sands 1 through 5 going across the landscape. So this is transect A, the seaward to landward transect. And then we also have the sand C following along. What was really unique was that once I started to draw these stratigraphic transects, so we have here these thicker ones are pits, and these thinner ones are cores. And the pits are thicker because we could just see the stratigraphy better. We were more certain about what we were seeing. What was unique is that after I started to draw out these transects, I found this yellow unit there, the sand 4B, that we didn't really recognize that out in the field. It didn't really quite match all 3 criteria for being a tsunami deposit. It didn't really follow further inland. It wasn't really thinning out. For that reason, I'm not definitively calling it a tsunami sand deposit, but I do recognize that it is a very unique sand deposit. So again, sand 4B. We have transect B. Again, that was the east-west-ish transect that was looking at the widespread nature of these units, and we find all 5 sand layers, including sand 6 there in the stratigraphy. What was additionally unique was I found another sand unit, sand 2B here. Not sand 4B, this one's higher up in the stratigraphy. Again, it didn't really match all 3 criteria, but it was a very unique sand layer, so we're calling it sand 2B. And do these eventually pinch out and disappear in the landscape? They do. So about 1.2 kilometers inland, they disappear completely from the stratigraphy. Grain size results seem to confirm that these sand units are in fact tsunami sands. So here we have grain size results taken from the sand units, sand 1 through 6. You can see here this is volume here on the y-axis, particle size on the x-axis. The curves are all relatively similar. So similar, in fact, that I was able to average all of these results and compare them to samples we took from other areas at Quirico. So 2 taken from the river channel, a couple taken from the beach, a couple from the dune, and a couple of the sediments that we were able to extract from the peat units. And you can see that the results show that the sands, the dune, the beach, and one of the river channel samples share similar grain sizes. And this would be expected if we thought that the sands were tsunami deposits, because the tsunami would flow overland, pick up whatever sediments it can, deposit them elsewhere. So there would be a lot of mixing going on. Alternatively, we see that the silts from the peat and from one of the channels are more strongly bimodal. Again, these are differences just due to mixing. As to why the river channels deposits might be a little bit different, it could just have to do with where I sampled them. Thin section analysis confirmed grain size analysis in that there was just a lot of mixing. So ultimately, all the thin sections shared similar mineralogical composition and were angular to subrounded. So they were all relatively the same, which again was to be expected. So can we put a timing to all of this deposition here at Quirico? We can. So these pink diamonds here show areas where I was able to get organic material to date for radiocarbon dating. So I'm going to start from stratigraphic bottom to top. Again, I couldn't get to the bottom of sand 6, so we do have a minimum age date for sand 6 at 1310 AD. Sand 5, we have 1430 to 1460 AD. Sand 4, 1670 to 1890. Sand 3, 1700 to 1960. Sand 2, I have constrained right at 1960 because the 1960 earthquake and tsunami was such a strong event. We hypothesized that sand 2 was from 1960, and we tested this by measuring for concentrations of cesium-137. This was really helpful to us because cesium-137 wasn't introduced into the atmosphere until 1950 AD. So if we hypothesized that the sand unit came at 1960, what we did was we tested the samples above, within sand 2, and below sand 2 for cesium-137. And what we found was that there was cesium-137 above, within, but not below the suspected 1960 tsunami sand, which confirmed our hypothesis. We also have sand 1 here pegged right at 2010 because we know the 2010 tsunami was the most recent. And interviews with the local residents, they said that indeed there was a tsunami, and the tsunami did in fact come into this floodplain and deposited sediments. So can we actually correlate these sands with these historical records that we talked about? And we can. So again, we have sand 1 at 2010 circled over here, sand 2 at 1960, sand 3 here at 1835. That's to help you here. Sorry about that. And we have sand 4 at 1751. Sand 5 we have is a newly discovered prehistorical tsunami. It's really well constrained with the radiocarbon dating, 1430 to 1460. But again, it precedes the historical records, so we think it's a pretty new tsunami. No one's talked about it yet. And we have sand 6 we hypothesize is potentially a paleo shoreline. So if the shoreline at Quirico were further inland, perhaps that's what sand 6 is. Again, I also mentioned these B sand layers, sand 2B and sand 4B. I didn't really do any laboratory analysis for these sands because unfortunately they were not in the sediments we took to sample. But if they were, based on the stratigraphy, to follow into this chronology, it's possible that sand 2B is related with the 1837 earthquake and tsunami, but that's uncertain again. And sand 4B could be any event from 1737 to prehistorical records. So it didn't really help us to confirm it, but it's possible. So on to the conclusions. So we have 3 major conclusions. There's evidence of 6 to 8 tsunami deposits within the last 800 years. We suspect this is the case because the sands are laterally continuous, but they do thin landward, disappearing 1.2 kilometers from the coast. Grain size analysis shows that the sand shares similar distributions to the beach, dune, and channel, and the intervening organic rich units are vastly different. Thin section analysis shows similar mineralogical composition. So second main conclusion, historical records cite at least 9 well-documented tsunamis since 1570 AD. Quirico shows evidence of about 4 tsunami deposits within this time period and an additional prehistorical event dated between 1429 and 1464. And stratigraphic evidence suggests Quirico selectively preserves large tsunami events from both the north and the south, but there's a possible bias towards events to the north. So you're super excited, and are there any questions? Yeah, Nick.
Good job, number 1. The sediments between the sand sheets. I'm curious if there's any evidence of land level change between those earthquakes. Like in Cascadia, we've got a major change in deposits.
Right, yeah, that's a really good question. We actually are on an NSF grant. Our co-PIs are diatomists, and so they will be doing diatom analysis to better constrain evidence of land level changes based on the stratigraphy. But first we had to get down the stratigraphy,
yeah,
and then they'll be doing their work from there.
questions for Isabel?
Yeah.
So you started out by your talk saying that we need to understand this to better mitigate tsunami hazards. How do you see this work helping mitigate tsunami hazards?
Well, if I can talk specifically for a moment, at Quirico it seems like there's a selective bias towards northern rupture, so maybe if there were a stronger earthquake that ruptured to the north, that's something for Quirico to maybe be more aware of than if perhaps there was a southern rupture. And as far as the bigger question, it's just a small piece of the puzzle as to better understanding how tsunamis are preserved and how we're able to better understand, how, if there are tsunamis, do they ever get preserved inland? And if so, what can you say about the magnitude of these tsunamis? So it's just a little piece of the puzzle, I think. Yeah.
Good answer.
Any other questions?
Yeah.
So how do you tell the difference between a tsunami and a giant storm event?
That is a really good question. It would have to be a mix of different proxies, looking at the stratigraphy, for example, for maybe differences in the structures. So storm deposits are often, they have more laminae because there are multiple events repeatedly inundating the area, whereas a tsunami will just have a few very strong pulses. Aside from that, people have tried with diatoms, but again, diatoms with storms, you can also be bringing diatoms in from the sea. It's possible that the shells are more fragmented, but again, there are always exceptions to the rule. So for now, it's mostly looking at the stratigraphy.
And is there a place in the world where they're like here, where you can actually do the active experiment of waiting for a giant storm, running out and sampling the, because maybe there's a grain size difference, or
Yeah.
some sort of, is that ongoing work in this area? Do you know, or?
There are people who have done extensive grain size analysis and statistics to develop a sort of envelope curve, trying to pinpoint, okay, if we know that the grain size from a storm can look like this, then possibly the provenance of these deposits could be storm versus tsunami. But again, like you said, it would very much depend on the site, so you really have to look for a storm to happen and then go sample those and wait for a tsunami to happen and sample those. So, yeah.
Yeah, it's tough to
Okay. Let's gather together again for our final presentation in this session. Diana Strictly and her faculty mentor is Ann Egger. And Diana will be talking about controls on fault geometry during early stages of extension in the Larkspur Hills Northwest Basin and Range.
Thanks for that introduction. This photograph is taken in my field area. It is of one of the Larkspur Hills, all of which are formed by normal faulting. So I was standing on the drop-down block looking up the fault scarp that is formed by the up-thrown block. This is in the tectonic setting of the basin.